Are you good?
Yeah, I'm good. Okay. Hi, everyone. I'm Joe Arnold, CEO of SwiftStack. What I'm going to do today, so what we do is we provide an object storage system. We're the leading contributor to OpenStack Swift, which is the object storage component out of OpenStack. And today, what I'm going to talk about is object storage and some of the use cases. And how we're going to walk through this here is I'm going to walk through some of the use cases that are required, or kind of set the stage for why there's a need for an object storage or cloud-based storage. And I'm going to walk through the different cloud computing environments, what it means, drill down into the architecture, so start a bit abstract, head down into some architecture. I'm actually going to touch on the key value drives, which Seagate announced a couple days ago, whom we've been working with, and then talk about some of the use cases. So I'll move through this pretty quickly. If you guys have questions, I'm doing this for you guys, not for me, so if you have any questions along the way, don't hesitate to ask. Of course, we all know 4 basic pillars of a compute environment, or of a cloud computing environment. You have the application itself, which needs to consume the resources, and those resources are compute, I have a job to do, network, I need to move data to run that job, and storage, place to store bits, so they can be served out later. The type of applications that at least we're facing with is they're changing a bit, in that more and more of the data is being served out to tablets, mobile phones, web applications, instead of necessarily residing on a local desktop or a laptop. And I figure it's an IDC graph of, hey, there's less laptops being sold. There's a heck of a lot more of mobile and tablet devices being sold. I mean, we're seeing that true. I think that drives some challenges in the data center as we start to scale up that infrastructure. And so there's a need for how storage changes in that context as well. So that's kind of the high-level vision slide of I think, some of the new challenges that we're facing. So we're building a compute environment. One of the things that's neat about compute is it can move around really quickly. You hear the concept of hybrid cloud, and what that actually means, what you can do is you can run a compute job in your own data center, and then you can ship another job out to a compute environment if you need to burst out. And that's easy to do when it's just bits of code that need to go execute. But then this pesky thing of the network gets in the way. And moving data around is more of a challenge, because you're having to figure out how to route data from one place to another. And we're seeing folks physically move data around when they need to do that. Sometimes that's the most efficient way. And there's an analogy between water and electricity with compute and storage, where storage is more like water because it just requires more infrastructure. You have these dams, you have the aqueducts. Moving it around from one cloud environment or for your own local environment is a lot harder to do through these little tubes that we have. Whereas the compute environments can burst out much easier, assuming the data is there. And so what we're seeing people do from a cloud perspective is that they have a tendency to want to have control over their data. And when they're doing that, they want to use open tools. They want to use open source software fundamentally to store their data, because they get more control over it. The key thing that we're seeing with the customers that we're working with is when they're building up the infrastructure in-house, they don't want a black box, because when things go wrong, they want to be able to open up, inspect it, not get locked into a single vendor. All the benefits of OpenNet, I think we know and love. So the different types of cloud storage. There's public environments, and I'm just using the example of Amazon as the de facto way to describe it. They have a product called EBS, they have a product called S3. They actually don't have a file product. which is kind of interesting. So you can only, in that context, you can only consume blocks and objects. Actually, I was one of the, a few years back in one of the companies I was at, Amazon invested in us. There was a company called Engineer. We were doing Ruby on Rails deployments at the time. And we were building out this platform on top of Amazon, and we were kind of freaked out by the fact that there was no file in that environment. And what ended up happening was that the application developers changed how they stored data so they could just store it in something like S3. So this was not too long ago where we saw the emergence of object storage and how these applications were put together. And so in the private context, when you start building that out, there's a propensity to want to have something that developers who are building these applications already know how to use. Something like S3 would be the equivalent of that. I won't spend too much time on this, but you can use the public cloud for these people building the applications, but there's a lot of motivation, and I think while we're here, there's a lot of motivation for people to build their own storage infrastructure in their own data center. And here's a few reasons why. So the good thing about the public cloud, and just listed a few here, Amazon, Rackspace, and SoftLayer, is that it's really easy to get started, but then it gets expensive once they scale up. And you also don't have control of your data because it's not in your data center. It's out in the open. You have to manage the accounts. You have to manage privacy around that. It's great, but I think there's an opportunity for private clouds to exist. So with deploying your own infrastructure, you can scale that up as you need. You have some cost certainty. You can own it, scale it. Do all of that. Does that make sense from a kind of landscape perspective? So the way that object storage works, though, is a little bit different than just a file or a file system. The way that it's put together is there's two components. There are logically two components if you want to think about it. One, that first component is a data ingest point. We call it, in our infrastructure, we call it the proxy server, but the point is that data comes into that part, and then it gets routed to other parts in the system, other storage nodes that exist in the system. And the benefit of this is that you can scale that component up independently from the storage. So if you need to handle a lot of ingest, you add more of in this tier, or we call the proxy tier. And then if you want more storage, separately you can scale out those components. And when there's a failure, and failure can exist either at the node level, the drive level, someone unplugs a network, then that top level knows how to route around, it knows how to load balance around the rest of the infrastructure. So we'll actually do things like stack rank which system is performing, which gives me the lowest latency, and send more requests to that node. So we can actually load balance across the rest of the storage system. I can create different pools of these things in other regions to load balance across. So then how it works at the individual storage level is, like most distributed storage systems or distributed databases, there's this concept of consistent hashing, and we call those things in our partitions. And each one of these nodes is responsible for replicating, checking for integrity of its replicas, and then just proactively replicating when there's a mismatch found. And this just happens all the time on every node, all the time. And then that way, when there's a drive failure or there's a system failure, we can raise the durability level up back to what it needs to be. Then there's a separate set of things that on the box that do auditing, and it actually picks up an object, says, "Hey, are you okay?" Checks a checksum, and will proactively throw things away if there's a failure on that individual file. What stitches all this whole thing together is something we call the ring, which is that consistent hash ring, which allows a request as it comes in to map to a specific storage node. And it gives every component in the system the same roadmap, if you will, about where data is placed in the system. So the only way you get data in and out of the system is with a URL, and then that gets mapped to those physical locations. There's some really cool stuff that we've had the opportunity to work with Seagate on around there's a new drive platform they have. It's called the Kinetic drives. And this is freaking mind-blowing what's been happening. So the drives actually speak Ethernet and key values. Yeah, isn't that cool? So instead of having a POSIX file system, which maps kind of down into the file system, where we're storing, a file system knows about sectors and where things are placed physically on the drive. That's completely the responsibility of the drive. And the way you communicate to the drive is with an API where you put objects into it. And then the way you communicate that is over Ethernet, over IP. And what that means is we can go from an architecture where you have a storage node with CPU, controller, RAM, network, a bunch of devices, power supply, power source, and a lot of that goes away. And what you're left with is a network switch, which lives inside of the box, and then the drives directly connected into that switch over Ethernet. It's pretty freaking cool. And then that all gets plumbed up to a top-of-rack switch. So it means, what it means is we can have an architecture where we can have the compute resources needed for the storage system deployed separately than the actual storage for the storage system. So if we need to be more responsive with replication, more responsive with auditing, handle more data ingest, we even have more of an advantage here because we can set up pools of these. I'm going to back up just a little bit. We can set up pools of the compute services just entirely separately from the storage, and we route requests to the storage over IP. Anyway, it's really, I don't think it can be understated how much of a revolution just doing that is going to make. It's a big sea change that's coming up. If you want to learn more about that, there's a developer kit with Seagate. I would just check it out at the very least. We have some resources that we've been working with them on. What I think that was neat to point out here is that on GitHub we actually have a working example of a storage system using these new drives that you can go take a look. So we're fundamentally an open source company, and we've implemented a driver to use these devices. So if you want to take a look to see what the API looks like, how it's used, it's a really great example of what that looks like.
Joe, you mentioned that you said that you're able to route to those drives. Is it actually doing like layer 3 type routing?
Routing. They have they DHCP. Right, and so the physical boxes. I mean, you have silicon. You basically have copper. Sorry, what's the manufacturing process of boards where you etch in copper? Those all get connected into basically a couple of Marvell, chips that are just switches. And then there's a couple of uplink ports. So each device is multi-homed. So then at the layer where we're routing requests down into those drives, if one of those nodes, any of the nodes in the system go down, because they're multi-homed, we're not going to lose touch with that device. And so the top of the switch becomes a concentrator for networking, and That's how it works.
Using traditional v4 IP, or is it using
either? Yeah. I mean, it depends. I mean, we're using V6, but V4 works.
Is there any integration with any of the SDN stuff to go along with it at this point that you're aware of?
Well, it's layer 3, right? So how much dynamic provisioning do you need of that network? It's an all-routed network. I don't need to create a private network for this setup.
Security-wise, you might want to.
Oh, sure, certainly, yeah, absolutely. You can put them on a VLAN, or you can physically isolate them. But that would be a separate concern than how the device works. That's something that we might care about as being a management and deployment and configuration engine. But from the device perspective, there isn't that concern.
So now, along this paradigm, so normally you have storage, and your compute goes and talks to storage. Do these drives check in to the compute? Because remember, they're DHCP.
That's right.
Be anything.
Yep.
Do they? Because you need to change that paradigm. Is that how they work? You don't know yet.
No, that is exactly how it works. They do check in. So in other words, to manage this infrastructure, you need to have DHCP services. Or you need to configure your static IP assignment to them.
Yeah, I don't want to do that. I want DHCP.
Exactly. You want DHCP, so you need to have.
I want to be able to couple my drives.
That's right.
To get different IP addresses, and I want my Swift
to work. That's right. So you actually have to have those types of services. And our perspective is we're just layering on those additional. I mean, we need to run Swift. We need to have DNS. We need to have a package repository for upgrades. We need to have a number of other monitoring service management services to run these distributed systems, and that just gets folded in as one of the other services that needs to be part of the system. Just to be sensitive of time, but feel free to ask some of the questions. But if you have a situation where you have multiple regions that you're setting up, now the device is dumb. Sorry, I didn't mean to. It's not dumb. It's very smart, but it's not aware of where it is. Now the services that interact with those drives need to be aware of what region am I in. And so when you have a request that comes in, say that I want to do a local write into an environment, and then I want to replicate later out to other environments, or if I get a request, I need to know where I am and ask for local copies of data rather than remote copies of data. And so that absolutely is part of the application that needs to be aware of how these drives are being used. Because what you're not going to see is the request go directly to that device and get certain direct server return style back up to the client. You're not going to see that. It's always going to go through some set of services that are responding to the client.
Do objects span multiple devices, or are they kept hold?
So the way we're doing it today is an object in the drive can be 1 megabyte large. And we are streaming multiple chunks into a single drive because we have a lot of knowledge about a device and dealing with the failure of that individual device. What we're working on now is the concept of using erasure codes, where each chunk will be distributed across that multiple drives in a similar fashion.
When you talk about replication, is it going to be that a region is all? So when we talk about replication and whatnot today, am I saying I'm going to take a snapshot, and the snapshot says all objects are going to be the same to this time frame, but because you have so many individual objects, is your replication all objects in one time frame, or each object individually to its own?
Awesome question, right? So you'll see that we'll have replication does have to change with this concept, because the drives, what we're not doing is mounting them and then copying files and whatever transport mechanism between them. What we do is we have a replicator that runs in the pool of compute services. So where Yeah, so here we'd have, we call it a replicator, but it's not really doing the replication. It's just checking for that there are replicas, and then what happens is it tells the drive, hey, you go copy your bits over here. And so the drives are actually talking to each other, and so then now that the fact that they are routed and not on a private domain serves to an advantage as you start creating systems with thousands and thousands of these devices out there, because you wouldn't want them all to exist on a private network. And then we also have a separate, because we can tell them how to communicate to each other, we can put them on, if they're in different regions, we can route them separately, so we can be smarter about using a more expensive LAN link between the devices. So, some neat stuff. These systems aim for concurrency. I don't know how to visualize that. This is the best I could come up with. Instead of handling one stream of I/O very well, which gets spanned across lots of devices, we actually are really good, and we're specially tuned for handling lots of simultaneous requests across lots of connections. And that's the use case that we're really good at.
A picture of Thanksgiving Day outside Walmart.
Exactly. Walmart is a very apt, it's an apt description. That's what we're tuned for. Everything has a URL. It's web addressable. Developers like it. It's very consistent to the cloud storage development paradigm. So you start seeing many tools that exist to support it, including things like the data movers of the gateways, file system clients. You'll see backup tools and all sorts of programming languages, of course, natively supported. Durability properties are very good. Lots of concurrency, and of course it runs on standard hardware. So even if you're not using the new kinetic type of drives, the existing infrastructure works really well too. So it's still a great model to install upon. And then we sit upon Linux, and that is going to be up to our customer's choice, whether it's Ubuntu or Red Hat or CentOS. We sit on top of those environments.
But knowing those are 7 nines of durability, how are you saying you're 7 nines of durability?
Because he's got all those compute nodes, so he can lose 1 or 2 or 3.
We can lose a lot of nodes.
Lose them all. Right.
I can show you the I'm trying to remember the URL directly, where we compute we use not drive reported MTBFs, but experienced MTBFs across a reasonably large system. Not a 5 terabyte system, but a several hundred terabyte system where we have broader fault tolerant domains, which is our typical deployment. So we can have a very low likelihood of a failure because we can recover relatively quickly when there's individual failure. That's what we got that from. Anyway, somebody else has to produce that, so we kind of put our heads to it and did that.
That's a number. I was just curious how you got the number.
Yeah, that's how we did it. It was a spreadsheet, and got it validated by a few more folks in the Swift community. Yeah.
On the last slide, how about putting it all together? I think Silicon Mechanics is here at the show. And
Silicon Mechanics is here at the show. They actually have some SKUs with that are form factored that we've shipped to many customers, and they will have those things pre-configured and ready to go with SwiftStack software on them.
including rack and network and all that.
Rack, network, yeah, of course, all that, everything you need to get that running. So are people using it? Yeah, there's people using it. So Concur, for example, is doing a globally replicated cluster with for their customers. So what they do is, if you've ever done expense reporting, you're likely to have run across them. You take a picture of your receipt with your cell phone, travel documents, things like that. They got a lot of users. They have a software as a service application that powers that. And what they're doing is they're doing a multi-region cluster, and then they route users to the nearest location so they can upload data quickly, and then asynchronously the data gets replicated to the other side. So it kind of serves two purposes. One is good user response, good utilization of the equipment at hand, and then in the failover case, they can just kick everyone over to one of the other locations and keep running.
Is that routing done by Swift, or is it done by on global network loadouts?
Both. So at the I'm trying to remember if they're using Anycast or there's some DNS services which will resolve a host to either one of those sites, and then the trick is when you go to fail. If you fail a request, you have the option to either kick it back up to the user, have them reroute them back over to the other site, or you can do that on the behalf of the request and go over that WAN link for them. And some users prefer one or the other, depending on what they're trying to achieve. But yeah, that's a good question to have. They're also a Windows shop. So we're an OpenStack company, but they're running SQL Server and C# and all that kind of stuff. They're in Seattle, so I can't blame them. But that's what they're doing. Disney, gotta get this. Disney is using us for a product called Disney Infinity, which is a kids game and user-generated content associated with that. And there's a lot of rendering data as part of the game development production that they're using. They're a Citrix Cloud platform customer. And so again, another example of different cloud environments. They have a storage need, they have a compute need. They're almost independent of each other when they're building out these applications. The other thing we did with them is they needed LDAP. And this sounds kind of like a strange thing for a storage company to worry about, but what I found, what we've been having to worry about is these integration concerns. So how do I have 100,000 users in an environment, and how do I plug back into the authentication system that I already have so I can charge them or build them or revoke access or put people in groups, and then they have group associated with the data. That's a lot of the type of stuff that we've been working on incorporating into the storage platform, and it just makes it just a whole integrated solution rather than a disaggregated thing of parts that they have to string together, and so that's one of the reasons why they went with us. There's an online gaming company that started in Amazon, actually. They got really big, went public, and then they go, oh shoot, we have to worry about cost. And that was a big incentive for them to bring back a lot of the compute work into their own data center. And we were part of that, helping them move to really just petabytes of data out of the environment and got it into their own environment. Broadcasting, instead of storing it on tape, put it on something that's actually has a URL, then you can do something with it. You can encode it, you can transcode, you can distribute it to other content distribution platforms, put ads around it. This is actually a sports network that we were working with. Again, another Microsoft environment. And then service provider. Have lots of users, you need to be able to build them. You need to have a multi-tenant storage platform to put them on. You need to replicate data, multiple sites, put storage policies around that. So what's next for us is being more flexible on where we put the data, and we've already started down this process by working with Seagate and swapping out different key value to work with the key value stores. We're absolutely open to working with other storage platforms underneath, because we are presenting data, an interface up to the application. We also have a couple of cool things like storage policies, so we can lasso together different types of regions or different type of storage equipment and put data on them. So if you're fast replicated or expensive storage and you're slow, stuff I don't care about over here, and you can actually have differentiated storage policies between the two. We're working with Intel and Box on doing erasure coding, so that can very much, as you mentioned, like as you're asking, it can reduce the amount of actual storage footprint for a storage infrastructure that's all co-located with each other. So that's the stuff that we've been working on. We've been making it just super easy to deploy, manage, operate, scale, keep track of all the metrics so that the operator can really easily manage a distributed system. That's what we're here to do. We got a book. I think we have a few more copies in the back. I think most of them went from the last session. There's like 4 more. But
you're going to be signing them, right?
Yeah, sure. Yeah, that's of course.
You can't sell on eBay though after it's signed.
That's true. That's true.
I was going to have them send it dear eBay buyer.
Anyway, so appreciate the time and attention. Thanks for the questions very much.
Joe, can you